Hello, my name is Mr. Whiteman, and in this video I'll be going through A-level energetics, Hess's law, specifically average bond energy calculations. So we're looking at the bond enthalpy. So the bond enthalpy is the enthalpy change to break 1 mole of covalent bonds in the gas phase, and you're usually presented with data as in the table. But it's important to recognise that these are endothermic. Endothermic changes are bond-breaking processes. So that is an arrow going up if we were to look at an energy diagram from our reactants to products. That is a positive change in order to do that. The level of maths that you need is something like this. So if you had a piece of string that was 100 centimetres and another one being 40, and you had another one that could measure up to each one like this, then what would be the length of the piece of string? The answer would be 60. As I don't mean to patronise you here, but this is the level of maths that actually you generally need when you do Hess's law and enthalpy calculations generally. But the important thing is to know your definitions. So here's a GCSE question, and you can pause the video should you wish to have a go, but I will go through the answer right now. So ethanol and oxygen make CO2 and water, and the bond enthalpy values are provided. And what you need to do, and what you probably would have done at GCSE, is to count how many of these bonds that you have. So a CH bond is worth 413 to break, and we have 5 of them. We have 1, 2, 3, 4, 5. A CC bond is 347 times by 1. A CO bond is 358 times by 1. An OH is 467 times by 1. And the O double bond O is 495 times by 3. So adding all that up comes to 4722. Doing the same with the products, the C double bond O being 799, and we've got 4 of them. You've got 2 lots of CO2, so that's 1, 2 to break the C double bond O bond, and you've got 2 of them, so it's another 3 or 4 when we break the other CO2. And OH is 495 to break, and we have 6 of them. And again, if you had 6 OHs, it's because you have 3 lots of waters, and this is usually the error at GCSE. So if you had 3 lots of waters, that's 1, 2, 3, 4, 5, 6 bonds that are breaking when you break waters OH bond. And then you probably were told something like energy change equals reactants minus products, energy change equals bonds broken minus bonds formed, energy change equals energy in minus energy out. And if you were to do this, either one would be the same result. 4722 minus 5998 will give you minus 1276. So the question is really, why is it reactants minus products? Do you understand what you're doing in this quick little calculation? Because sometimes people get confused when you're later told that the delta H formation of products minus delta HF formation of reactants, and the sum of, would give you the enthalpy change of reaction. So you might be thinking, when do you do products minus reactants? When do you do reactants minus products? What's actually going on here? And do you understand what you're actually doing in your calculation? And so what you're actually doing is, like I said, with that piece of string. So our reactants are at this level arbitrarily, the ethanol and oxygen, and CO2 and water will be at the bottom because it's exothermic. I know it's going down, but I wouldn't necessarily have needed to have known that to have placed it there. And we're trying to work out that unknown root. If we were to break all the bonds in our reactants and all the bonds in our products, we would get to an energy state where all our bonds are broken. It'll be the same state because we have the same number of atoms in both our reactants and products. If the breaking of reactant bonds is 4722 and the products is 5998, that must mean the products must have started lower in comparison to reach the same energy level, and therefore that is our piece of string, and we're trying to work out that unknown, which is going to be 1276 as a change. But if you do reactants minus products, we get negative minus 1276. If you did products minus reactants, you'd have got a positive value because you would have worked out for the reverse reaction. So the maths would show you that if you do reactants minus products, we are looking at the energy change for the forward reaction. So to apply this to Hess's diagrams, there's Hess, we need to understand that there is 3 reactions that are taking place, and there could be more. So delta H1 would be the energy change between A and B making C, and that would be taking consideration of enthalpy change delta H2, delta H3, delta H4. We can use these values independently to work out delta H1, and it could be because we can't measure this directly, and by knowing an alternate route we could actually calculate that. So that's where it can be of use. So Hess's law is the enthalpy change of a chemical reaction being independent of the path taken. So our average bond energy data calculation, our reaction 1 was the combustion of ethanol, making CO2 and water. Reaction 2 is breaking all the bonds in our reactants, and reaction 3 is breaking all the bonds in our products. So we have to appreciate that there is a relationship that links them all together. And so reaction 1 was the route that I was needing to investigate. Reaction 2 was breaking all the bonds in my reactants. Reaction 3 was breaking all the bonds in my products. And my piece of string was 5998 in length, so to speak. Hess's diagram would be something like this. We normally write the reaction to be investigated or calculated horizontally, and then that would be our reaction 1. By definition, this is the enthalpy change of combustion, delta HC, because I am burning 1 mole of reactant. Reaction 2 is to write reaction 2 making all bonds broken, and that was 4722, and my arrow is going in this way because that is my reactants becoming products, and some people will get these arrows the wrong way around. To break all the bonds in my products would be reaction 3, and they are linked because they all make products where all bonds are broken. And so by knowing that route, we can therefore work out reaction 1 in its energy change, similarly to that of my piece of string was 5998, and then if I know the total distance, and I know part of it at 4722, I can therefore work out 1276, but it would be minus 1276, so the sign is also important, and that's why we do reactants minus products. You might have also been told that if you go round this way around the Hess law diagram, you can work it out as well, and it is true. So if you did plus 4722, and because we're now going the opposite way of the arrow, we reverse the sign, so that becomes minus 5998, so 4722 plus minus 5998, or just minus 5998, would give us minus 1276. So we can calculate it via Hess's diagram, appreciating that when we're doing that, all we're doing is working out that piece of string length. And that can be applied to all enthalpy calculations. That is all you're doing. So here's an exam question. So you might want to pause the video on the exam question, but I will then also go through it. So the exam question is on the screen. Ethane thiol is a compound with a structure similar to that of ethanol. This is for an A-level question, by the way. Unlike ethanol, it has an unpleasant smell that can be detected in very low concentrations by human. Who cares? For safety reasons, it's added to gaseous, odourless fuels such as propane, so that fuel leaks can be detected. When the fuel is burned, the gaseous ethane thiol undergoes complete combustion to form the oxide CO2, SO2, and water. And then we have some mean bond enthalpy data in table 1. The most important thing is to be able to write equations, because if you are unable to do part 1, which says write the equation for the complete combustion of ethane thiol, then that's going to make your answer in part 2 incorrect, but you get a transfer of error. Where possible, use your equation and data from table 1 to calculate the enthalpy change for the combustion of ethane thiol. So again, you might want to pause the screen should you wish to have a go yourself. But here's the answer. When the fuel is burned, you make CO2, water and SO2, and it's important to recognise that SO2 is there because a lot of people are just making CO2 and water. And so you would have got an equation by the inspection method where you're balancing the equation, something like this. Knowing it displayed or bond shown is useful for when it comes to breaking bonds, and this is an added challenge. So if you're unable to recognise how many bonds stuff makes, then that's going to probably affect your calculations here. So you need to be able to recognise, for example, carbon forms 4 bonds and oxygen forms 2. You might have got this as well, where you've got 2, 9, 4, 6 and 2 as a ratio. And if you've got that, then that's 1 mark for this. However, it's important to recognise that in the next part of the question, that would actually be a problem, because delta HC, enthalpy change of combustion, is the energy change when you burn 1 mole of a fuel reactant. And so having 2 of these would double your energy change, and therefore needed per 1, which is quite important. So if we carry on as if it were like GCSE, we're counting all the CH bonds that we have. So CH value times by 5, CC times 1, CS times 1, SH times 1, and O double bond O times by 4.5, we get 5276. Do the same for products. C double bond O times 4, S double bond O times 1, OH times 1 is 7050. And so therefore, if reactants breaking all bonds is 5276 and products is 7050, it must have started lower down in energy, which must have meant that when reactants become products, it has lost energy as it has become products, as it transferred energy into the surroundings, and it's exothermic, it's lost minus 1774 kilojoules per mole of energy. And if trying to draw Hess's law, then it would be something like this. So if we were to break all the bonds in the reactants, we get to an energy state where all bonds are broken. If we were to break the bonds in the products, we get to an energy state where all bonds are broken, which would be the same. The reactants reaction is 5276 and the products is 7050. And so again, you could be going around the Hess's law diagram, so 5276 against the arrows, it becomes minus 7050, and we'd get the same answer as minus 1774, or we could have done reactants minus products. And there we are. Thank you, and if you'd like further chemistry support, check out some of the other videos.